Hello, today we shall discuss mean field theories and beyond for accurate treatment of the electronic problem. Consider the electronic Hamiltonian, which consists of the kinetic energy of electrons, a one electron operator, the potential energy of electron nuclear Coulomb attraction, again a one electron operator, and then the potential energy of interelectronic repulsion, which is a two electron operator. Now here's where the problem comes, because as long as the Hamiltonian has only one electron terms, we can put electrons into one electron orbitals, solve the equations of motion for each electron separately, take the product of the one electron orbitals to form the total wave function, and sum up the orbital energies to get the total energy. But with this two electron operator, that's where the problem comes. So let us define the core Hamiltonian by collecting together the one electron terms for each electron. So for electron I, the core Hamiltonian consists of the kinetic energy operator and the electron nuclear attraction terms for electron I. Then the electronic Hamiltonian is the sum of all the core Hamiltonians for each electron plus the interelectronic repulsion term. Let us write the wave function as a simple product of one electron orbitals, or the Hartree product, by putting electron 1 into orbital A, electron 2 into orbital B, electron 3 into orbital C, etc. until electron n into orbital K. We shall worry about indistinguishability and antisymmetry later. Then the total electronic energy is the sum of the terms involving a single orbital at a time plus the terms involving pairs of orbitals. So here we have converted the summation over electrons I, J, etc. into summation over orbitals R, S, etc. HCRR is thus the matrix element of the core Hamiltonian for orbital R, that is integral psi r star of I, hc of I, psi r of I, d tau I. And JRS is the Coulomb integral, or the Coulomb repulsion between electron I in orbital R with electron J in orbital S. Now psi r star of I times psi r of I is rho r of I, the density of electron I in orbital R, and psi s star of j times psi s of j is rho s of j, the density of electron j in orbital S. So JRS can also be written as integral d tau I integral d tau j rho r of I times rho s of j by Rij, that is the Coulomb repulsion of electron I in orbital R with electron j in orbital S. So JRS is the average energy of interelectronic Coulomb repulsion between electron I in orbital R and electron j in orbital S. And JRS can also be written as the matrix element of a pseudo operator known as the Coulomb operator Js of I. But of course we have to respect antisymmetry, and so we cannot just write the wave function as a simple Hartree product, but we have to write it as an antisymmetrized product of spin orbitals, that is as a Slater determinant in this form. So here psi a alpha, psi a beta, etc. are one electron spin orbitals, and A, B, etc. represent two electron orbitals, each of which can take an alpha electron and a beta electron. Okay. The energy contribution due to the core Hamiltonian is now twice the sum over the spatial orbitals of HCRR. And the electron repulsion terms arise from two electrons in the same orbital as well as two electrons in different orbitals with the same spin and two electrons in different orbitals with different spin. The electron repulsion between two electrons in the same orbital can be written as this. So this is the antisymmetrized product in the bra and the antisymmetrized product in the ket. So we'll have terms arising from the product of the first term in the bra with the first term in the ket, and the second term in the bra with the second term in the ket, and that gives JRR. The product of the first term in the bra with the second term in the ket, and the second term in the bra with the first term in the ket are 0 because of spin orthogonality, because alpha spin is orthogonal to beta spin for each electron. Electron repulsion between electrons in different orbitals includes those with the same spin, that is repulsion of alpha electron with alpha electron and beta electron with beta electron, and those with different spin, that is alpha electron with beta electron and beta electron with alpha electron. If we take the latter first, the electron repulsion between different spin electrons in different orbitals gives us the Coulomb integral JRS. Okay, so working through the algebra just as before, we will get JRS for this as well as for this. Other terms in here arise are again 0 because of spin orthogonality. Okay. Electron repulsion between electrons in different orbitals are not equal to S with the same spin, that is alpha with alpha and beta with beta, now gives us an additional term minus KRS because of the product of the first term in the bra with the second term in the ket, and the product of the second term in the bra with the first term in the ket. Now there is no vanishing due to spin orthogonality. There is no spin orthogonality here because they are all alpha spin. And similarly for the beta spin repulsions, we'll get another GRS minus KRS. So now there is no vanishing of terms due to the spin orthogonality, and we have an additional term KRS, which is known as the exchange integral. Okay. So collecting all the terms we have obtained for the Coulomb repulsion of orbital R and orbital S, we have JRR for the repulsion between the two electrons in orbital R, JSS for the repulsion between the two electrons in orbital S, one JRS for the alpha R beta S repulsion, and another JRS for the beta R alpha S repulsion. Then one JRS minus KRS for the alpha alpha repulsion between R and S, and another JRS minus KRS for the beta beta repulsion. Okay. So summing it all up, we have the electronic energy is equal to twice sigma R HCRR, the sum of the sum of the core Hamiltonian integrals, plus twice sigma R JRR plus twice the sum over the pairs RS, 2 JRS minus KRS, where HCRR is the matrix element of the core Hamiltonian in orbital R, JRS is the Coulomb integral, and KRS is the exchange integral. As we already saw, the Coulomb integral is the average energy of interelectronic Coulomb repulsion between an electron in orbital R and an electron in orbital S. The exchange integral KRS, however, has no classical analog. Note, however, that both the Coulomb and the exchange integrals depend upon the orbitals psi r and psi s. As we saw, the Coulomb integral can be written in terms of a Coulomb pseudo operator Js, which represents the average Coulomb potential felt by electron I due to electron J in orbital s. Okay. Similarly, we can define an exchange pseudo operator Ks. Our task, therefore, is to find the orbitals that diagonalize what is known as the Fock operator after Vladimir Fock that is F equals Hc of I plus twice sigma S Js of I minus sigma S Ks of I. But as we saw, both the Coulomb operator Js and the exchange operator Ks themselves depend upon the orbitals psi s. Thus, we need to find the orbital psi s by diagonalizing the Fock operator F, but F contains Js and Ks, and in order to evaluate Js and Ks, we need to know psi s. That is, in order to find the orbital psi s, we need to know the orbital psi s. So we need to adopt an iterative procedure. So to find the orbitals that diagonalize the Fock operator, we thus have to employ an iterative procedure with an initial guess for either the orbital psi s or the Fock operator F. So to outline the iterative Hartree-Fock self-consistent field procedure or SCF procedure to find the orbitals that diagonalize the Fock operator F, we start with an initial guess for the set of orbitals. We call it psi s of 0. Using this, we construct the operators Js of 0, Ks of 0, and F of 0. Or alternatively, we can start by guessing an approximation to the Fock operator F of 0. We diagonalize F of 0 to get a new set of orbitals psi s of 1. We use these orbitals to construct an improved Js of 1 and F of 1. We now diagonalize F of 1 to get a new set of orbitals psi s of 2. Use these orbitals to construct an improved Js of 2 and F of 2, and continue this iterative procedure until F at iteration I is approximately the same as F at iteration I plus 1, and all orbitals psi s at iteration I are approximately the same as the orbitals psi s at iteration I plus 1. That is, until both the orbitals and the effective potential are unchanged from one iteration to the next. The orbitals are then said to be self-consistent. The corresponding eigenvalues epsilon s are called the orbital energies. That is, these are the eigenvalues of the Fock operator. F operating on the SCF orbitals psi s gives epsilon s times psi s. Thus, we start with the core Hamiltonian, which consists of the kinetic energy of electron I and the Coulomb attraction felt by electron I to all the nuclei. We use that to construct the Fock operator, which consists of the core Hamiltonian, the Coulomb operator, which is the average Coulomb repulsion felt by electron I due to all the electrons in other orbitals, and the exchange, which has no classical analog. Diagonalizing the Fock operator gives us the SCF orbitals psi r and the orbital energies epsilon r. So the orbital energies are the eigenvalues of the Fock operator, and noting that JRS equals JSR and JRR equals KRR, we can show that the Hartree-Fock self-consistent field energy is given by E equals twice sigma r HCRR plus sigma r sigma s 2 JRS minus KRS, and that can also be written as E equals sigma r HCRR plus sigma r epsilon r, or it can also be written as E equals twice sigma r epsilon r minus sigma r sigma s 2 JRS minus KRS. The important point to note is that the total energy is not just the sum of the orbital energies epsilon r. So we have seen that the wave function for a closed shell 2n electron system can be written in the form of this Slater determinant, and its Hartree-Fock self-consistent energy for this 2n electron system is twice sigma r HCRR plus epsilon r. Now we can form a 2n minus 1 electron cation by removing an electron from orbital k. So here we have removed the beta electron from orbital k, and the energy of this 2n minus 1 electron cation is twice sigma r HCRR plus epsilon r minus epsilon k. We can also form the 2n+1 electron anion by adding an electron into orbital m, into a previously empty orbital m. And the energy of this 2n+1 electron anion is twice sigma r HCRR plus epsilon r plus epsilon m. Comparing these three energy formulas, we can see that E plus minus E, that is the energy of the cation minus the energy of the neutral, equals minus epsilon k, or minus the orbital energy of the orbital from which the electron was removed, and E minus minus E, that is the energy of the anion minus the energy of the neutral, equals epsilon m, the energy of the orbital into which the electron was added. This is known as Koopman's theorem. So Koopman's theorem can be stated as E plus minus E equals minus epsilon k, and E minus minus E equals epsilon m. That is, the ionization potential is the negative of the Hartree-Fock orbital energy from which the electron was lost, and the electron affinity is the orbital energy of the virtual or unoccupied Hartree-Fock orbital into which the electron was added. Yaling Koopman switched from physics to economics, where he applied his knowledge of optimization theory and went on to win the 1975 Nobel Prize in Economic Sciences for his contributions to the theory of optimum allocation of resources. As we have seen, the Coulomb repulsion JRS is the average interelectronic Coulomb repulsion energy between electrons. But in the exact Hamiltonian, this 1 upon Rij is the instantaneous potential energy of interelectronic repulsion between electrons I and J at any given instant of time. This is always less than the average repulsion because electrons avoid each other more efficiently than approximated by Hartree-Fock. Consider the dancers in the following video. So you are at this party where there are a lot of people dancing, and you have a plate of food in one hand and a drink in the other, and you're trying to make your way across the room to your partner on the other side of the room. If you just calculate the average positions of all the dancers and use that to navigate your way across the room, you're very likely going to bump into several people on the way, and very likely you're going to spill your food or drink. But if instead you track the actual instantaneous positions of every dancer and use that to avoid them and make your way across the room, you're very likely going to be able to succeed without spilling anything. So the Hartree-Fock theory, which considers the average interactions, overestimates the actual interelectronic repulsion. The true energy is always lower or more negative than the Hartree-Fock energy. This tendency of the electrons to avoid each other better than in a mean field description is known as electron correlation. And the difference between the exact non-relativistic energy and the Hartree-Fock energy is known as the correlation energy. So the correlation energy is the exact is the Hartree-Fock energy, minus the exact non-relativistic energy. So the correlation energy is the Hartree-Fock energy minus the exact non-relativistic energy, and this is always a positive quantity because the Hartree-Fock overestimates the repulsion and is therefore higher in energy than the exact energy. The electron correlation has actually two origins. One is the incomplete treatment of the tendency of the electrons to avoid each other in the Hartree-Fock theory, which is what we discussed, and that is called dynamical correlation. And this is actually well approximated by density functional theory, which we will talk about in another episode. The other origin of electron correlation is from the failure of the single slater determinant expansion to represent the true wave function, and this is known as non-dynamical correlation. And we have seen this in the case of curve crossings or avoided crossings, particularly acute in open shell systems, transition states, and curve crossing problems. So when the two potential surfaces come close to each other, then the single determinant approximation fails, and in that avoided crossing or crossing region, that is known as a high configuration interaction region. So the type of correlation that arises due to the correlated motion of electrons, that is due to the incomplete treatment of the tendency of electrons to avoid each other in Hartree-Fock theory, is known as dynamical correlation. For instance, in-out correlation is the tendency of one electron to be closer to the nucleus in an atom, whereas the other electron is farther away from the nucleus. And left-right correlation is the tendency of one electron to be on one side of the atom or molecule, say the left side, and the other electron being on the other side. And this can be well approximated, as we saw, by density functional theory. The type of correlation that arises due to the failure of the single determinant approximation to represent the true wave function is known as non-dynamical correlation, and it can only be handled by a multi-configuration treatment, for example, configuration interaction. Okay. And both types can be handled by configuration interaction or coupled cluster approaches. Okay. So what is configuration interaction? As we saw, the ground state configuration for a closed shell to an electron system can be written in this Slater determinant form. We can form an excited state configuration by promoting an electron from orbital K to orbital M. Okay, so this alpha electron from orbital K has been promoted now to the orbital M. Okay. Excited state configurations formed by promoting two electrons, say from orbital K and orbital J to orbitals M and N. These are known as double excitations. Okay. If we form all such single and double excitations and mix them in with the ground state with mixing coefficients to be determined variationally, that is known as configuration interaction singles and doubles. So if we just use single excitations, that is known as CI singles. So we have the ground state configuration for the 2n electron system, the excited state configuration formed by promoting an electron from orbital K to orbital M is shown here, and we generate all such single excitations from the ground state or from a set of reference configurations and mix them to form an excited state wave function with the mixing coefficient CKM to be determined by variational minimization. This is CI singles. If we form all single and double excitations from the ground state and mix them in with the ground state with mixing coefficients C, K, J, M, N to be determined variationally, that is Ci singles and doubles. So we have the ground state configuration, we have single excitation from the ground state, from all such single excitations. We have double excitations from the ground state, Kj to Mn, from all such double excitations. Mix them all in with these mixing coefficients Ckm and Ckjmn to be determined variationally. That's Ci single. So in the Ci procedure, we use the Hartree-Fock self-consistent field orbitals to construct antisymmetrized Slater determinant configuration state functions, then expand the Ci wave function in a basis of such determinantal configuration state functions. Often a very large number of configurations are required for accuracy. Next, we solve the secular equation sigma I Ci Hij minus E Sij equals 0, where Hij is the matrix element of the Hamiltonian between the configuration state functions, and Sij is the overlap matrix between the configuration state functions. For these linear equations to have a non-trivial solution, the secular determinant, that is the determinant of Hij minus Esij, has to be equal to 0. Typically, million by million or larger matrices are often diagonalized during Ci procedure. The advantages of Ci are that full Ci is formally exact in the limit of a complete basis set. It is generally applicable, that is, you can use it for ground states, excited states, for dynamical correlation, non-dynamical correlation, and it's highly accurate and is the state-of-the-art method for benchmarking all other types of calculations. The disadvantages are that a truncated Ci expansion suffers from size consistency and size extensivity problems. Full Ci is impractical except for very small bases, and even a truncated CISD and CCSD expansions are very computationally intensive, scaling with the fourth power of the number of electrons. When we expand the Ci wave function psi in a basis of the configuration state functions phi I, note that both psi and phi I are n electron wave functions, where n is the number of electrons. Bra psi psiket gives us the number of electrons n by normalization, and that is a scalar. And this is actually a short form for taking the many electron wave function psi, multiplying it by its complex conjugate, and integrating the product over all n electrons. Okay. If, however, we take psiket multiplied by bra psi, that gives us the density matrix. In the matrix notation, bra psi is a row vector, whereas psiket is a column vector, whereas C1, C2, C3 are the coefficients of expansion of psi in terms of the configuration state functions. And the product of this row vector times this column vector gives us a scalar n due to normalization. So 1 by n matrix times n by 1 matrix gives us a 1 by 1 or scalar. The density matrix is formed by taking the psiket, that is the column vector, and multiplying it on the right by bra psi, the row vector. So we have an n by 1 matrix times a 1 by n matrix gives us an n by n density matrix. Okay. So what is the physical meaning? Psi star psi is the simultaneous probability of finding an electron at R1, another at R2, etc. Until an electron at Rn. The reduced 2-electron density or pair density is obtained by integration of psi star psi over n minus 2 electrons. Thus, gamma of R1 and R2 is psi star psi integrated over d tau 3 till d tau n. The pair density represents the simultaneous probability of finding an electron at R1 and another at R2, irrespective of where all the other electrons in the system may be. The reduced 1 electron density, or electron density for short, is obtained by integration of psi star psi over n minus 1 electrons. That is, rho equals integral psi star psi integrated over d tau 2 till d tau n, which is, and you can also obtain this by integrating gamma of R1 and R2 over d tau 2. So rho of R represents the probability of finding an electron at R irrespective of where all the other electrons in the system may be. Similarly, from the full n electron density matrix, psi-ket bra-psi, the reduced 2 electron density matrix can be obtained by integrating this full n electron density matrix over n minus 2 electrons. And the reduced 1 electron density matrix, or 1 RDM, can be obtained by integrating the gamma over n minus 1 electrons. Okay. The orbitals that diagonalize the 1 electron density matrix, or 1 RDM, are known as natural orbitals. The corresponding eigenvalues are the occupation numbers. For a closed shell Hartree-Fock wave function, the occupation numbers are all 2 for the occupied orbitals and 0 for all the virtual or unoccupied orbitals. For CI wave functions, where you are mixing different configurations, the occupation numbers are in general non-integral. Okay, since the CI wave function is formed by mixing electronic configurations with different occupations. Occupation numbers for core orbitals are always very close to 2. Occupation numbers will vary very sharply in a curved crossing or avoided crossing region. For instance, here we have formed the CI wave function by mixing in different configurations, phi 0, phi 1, phi 2, phi 3 with different coefficients. The ground state configuration, psi 0, has all occupation numbers equal to 2 up to the HOMO, and all occupation numbers from the LUMO onwards equal to 0. Phi 1, phi 2, phi 3 are formed by excitations of electrons from the occupied orbitals to the unoccupied orbitals. And when we add up all of these, we get non-integral occupation numbers in the CI wave function.